Hello, relativity friends. Some time ago, I posted a playlist which I called Vectors and Tensors in General Relativity. Uh, I got an interesting question here. What does this playlist have to do with general relativity? It's a good question. Uh, I'll try to explain it. The playlist came from my notebook when I decided to study general relativity. I had to start from the beginning. I had to start with what is a vector. I hadn't seen a vector in about 40 years, so I did actually start from the beginning. And that notebook got really thick. I worked on this for a long time. And when I was finished, I said, wow, rather than toss this in a dumpster, why don't I post this so someone else may get some use out of it? Because there was a lot of information in there. So the playlist ends with calculating the Riemann curvature tensor, the Ricci tensor, and the Ricci scalar for what's called the two-sphere problem. Now, these tensors, Riemann tensors, Ricci tensor, Ricci scalar, these tensors are used in general relativity to solve Einstein's the field equations. But this problem specifically is very good for students to learn how to use all of the tensors indexes and such because it greatly simplifies the problem by saying that the radius of a sphere is held constant. And so you only got two variables. The theta variable is the angle from the North Pole to the equator, as example. The phi angle is the angle that swings around the equator. So this would be as though you're walking around on the surface of a sphere measuring curvatures called intrinsic curvature, Riemannian curvature. Okay. So this problem allows the students to learn how to convert Cartesian the coordinates to spherical coordinates, how to derive the basis vectors, ER, E theta, and E phi, how to use those basis vectors to find the metric tensor and spherical the coordinates, how to use that metric tensor to find Christoffel symbols for a sphere, use a Christoffel symbol to find the Riemann curvature tensor, how to contract that tensor to find the Ricci tensor, and how to contract the Ricci tensor to find the Ricci scalar. So it is a lot. It is a lot. And it's very, very good practice and a way to work with tensors so they're not so overly complicated to start with. Okay. But having said all that, the exercise is consistent with Einstein field equations. Let me show you what I mean. Okay, here is the Einstein field equations uh, minus the cosmology bit because we don't need it. So in general relativity, there are four dimensions, one of time and three of space. So these tensor components, this is a 4 by 4 the matrix, a 4 by 4 matrix, and a 4 by 4 the matrix. Okay. R is the Ricci scalar, it's a constant, and these are a bunch of constants as well. So the two sphere problem begins by assuming that the energy, stress energy momentum tensor, this guy is zero. Because we're not doing anything. We're not studying gravity. We're just walking around on the surface of a sphere because we're interested in this half. This half has to do with curvature. Okay. So that's what the problem was designed to be. I assume. I don't know who came up with it, but it's a good problem. It's fun. So there's only two dimensions that we have to deal with. So these guys become just the 2 by 2, the matrix. Okay. So in matrix notation, it looks like this. So the stress energy momentum tensor becomes zero. And so we just have this left, and these become 2 by 2s, right? So now and these cross elements here, the off diagonal elements are all zero. So we're actually just left with two equations, and it looks like this. So this element of this matrix minus with these scalars times this equals zero, which is this one. This component minus these scalars times this component equals this equation. So we know all of these because that's what we did in that playlist, right? And they look like this. So the off diagonals are zero. These are the two non-zero items, theta, theta, phi, phi. And for the metric, the tensor, it was, so A is the constant radius, okay? It could be any radius you want. It could be the radius of a basketball or the radius of the earth. It doesn't matter. A squared sine squared theta. Okay, so we take that information. Oh, and the Ricci scalar we found in that playlist was 2 over a squared. I'll leave a link to that playlist. I don't know if I said that yet. Okay, so here's the equation. We take the stuff from above. The 2's cancel out, a squareds cancel out. 1 minus 1 equals 0. So it's consistent. And here's the other equation. We take the stuff from above. The 2's cancel, a squareds cancel. Sine squared theta minus sine squared theta equals 0. Okay? So it is consistent with the field equations, although it doesn't have anything to do with gravity. It's just an exercise for students. Okay? I hope that helped. Let me know.